Welcome to the second of our series of BSUG this year. I do a quick introduction to a couple of little changes. For those of you who have been here before, are familiar with the lab and what I'm part helps fund little update. I'm Elizabeth Cooper, I'm the Director of Integrated Design Lab. We'll have our speaker today is Tim Johnson from CTA, and I'll talk about in just a moment. This is the current lab focus here. We've got a group of architects and engineers that put together some great outreach, research, and education on high performance building and building sciences generally. This is new, just sent out to print handle our commercial industrial program. It was newly branded with new construction retrofits, custom projects, FlexPeak, and can find more about those programs they offer and incentives and what they can help with their website. Another project that we do here at the lab is our building metrics labeling website tool, which allows owners, operators, managers, tenants to get a benchmark for their projects for UI, Energy Star, which also includes walkability and daylight for a single space. So why don't you check that out? See how your building compares to others in the area. We also have an extensive tool library here. Tools to test all things from power and energy to fluids and sound, light, all tools available free in the idle power territory. So check that out, see if there's something that you've always wanted to know about your building. Can help you figure that out, and soon I will be adding some books and other resources to the site, so you don't have to buy all those Illuminating Engineering Society books or all the current ASHRAE manuals. We'll have those available to them. So BSUG 2.0, today for Tim. Next month, we invited Pahranagat from Selena, a group out of Wisconsin, to talk about daylighting tool for rhinos. And then in August, David Rudd is going to come and talk about modeling and transits. Then we'll check back for the next couple speakers. A little incentive to all of you who are every once in a while about when you read these things, and I'm going to get 30 minutes. But how to read out of the 6 and put your name in the hat for drawing your history game. Do 4 out of 6, you get another try. So a little fun at the end of the year. So hopefully I will be able to make more than today. So welcome to Tim. Been working at CTA for about 9 years now. I'm an engineer there. There's a lot of energy modeling work for CTA here in Boise, and maybe for their other branches too. I'm sure you can talk about that. Originally came out of North Dakota State. Probably know what's your motto? What's your mascot?
Bison.
Okay, Bison. Yeah. Powerhouse team this far.
5 straight championships.
So thank you, Tim, and I'll let you go there.
Okay. Give kind of an overview of energy modeling. We talked about it kind of a mindset more than this is where you put this value, that sort of stuff. I think a lot of you have probably seen bits and pieces, but I think there's some new faces out here.
Let's keep it real informal. If you guys have questions, we'll stop here and there, and we can talk things over if there's questions we want to address in more detail. Interesting. Okay, so start of every presentation, got to ask why are we modeling? And I think if you've worked with us before, you realize it's because we're really, really ridiculously good looking, right? Here's a shot of our modeling team at CTA. But I mean, seriously, I kind of break it into design and then the post-design. And what I'm going to talk about today is mostly on the design side of things. We can talk a lot about post-design, modeling for lead, code compliance, things like that. But I think we're most effective in the design phase, so that's where we'll focus. Sometimes one of our requirements in research and development will dictate some of these things too. So this is kind of what we're going to go through. Sorry if you can't read it from the back, but I'll start with kind of some frontiers that I'm seeing in the energy modeling world, where we're headed, some new technologies and things. Software notes can be kind of overwhelming dealing with all the software. And we'll get into, starting with designing just a legal building. There's codes out there to dictate that, and then how to set some goals beyond that. And then navigating the rapids of energy modeling. I have all sorts of analogies I use every time, I apologize. We'll get into sensitivity analysis and load reduction, system selection, get into design refinement, and then the final documentation, and then following that up, and then a case study at the end. So the frontiers, there's a lot of research and development going on. ASHRAE has a lot going on. Here locally in the IDL, there's a lot of cool stuff. Damon's presentation last month was a good example. You really just got to go out and look for it. A lot of technologies are being used out there but aren't well documented in terms of performance. So we need to stay in touch with those things. A lot of national labs. We've had a couple opportunities to work with NREL to do some cool R&D stuff. Tools online if you're interested. And then the building information modeling, BIM, and the building energy modeling, interoperability. I think that's the next big thing. Autodesk and others are doing a lot to make that transition a little more smooth, but it still has some issues. And then the idea of sensitivity and parametric analysis. We have these fast computers, we've got cloud computing technologies. Why do we keep running one simulation at a time? We can run hundreds, thousands, and come up with an automated solution a little bit better. And we'll talk a little bit about that a little later on. All right, software. Overwhelming all the different options. I think two of the main categories are the DOE-funded softwares, the DO2, which was developed, I think, in the 70s or so. It's kind of a little bit outdated, though they continue to keep updating. I noticed DOE 2.3 is in its beginning stages, so there's that one. But the DOE is putting most of its focus on Energy Plus, and they've developed Open Studio as well as Symergy. Two different labs have different interfaces for that. So those are the two big ones. There's a lot of third-party interfaces for Energy Plus. There's Train and Carrier and IES all have good packages. My thought on software is that it matters more how well you can use the program than the program's capabilities. Things like eQuest, I do find limitations in what it can and can't model, so there is some of that, but a lot of it comes down to familiarity with the software, in my opinion. All right, how do we design a legal building? There's codes for everywhere. IACC and ASHRAE 90.1 are usually equivalent in most states. Here's the map of the United States. Currently in Idaho, we're on 2012 IACC, corresponds with ASHRAE 90.1. At the beginning of any project, or even down the road, you can decide which one you're going with, and each has its pros and cons. I generally find 90.1 to be a little bit less stringent than IACC, but they require occupancy sensors on plug loads, and they have a couple little quirks in there. Won't get into that too deep right now, but just be aware of that. And then 90.1 2013 and IACC 2015 are coming, well, they're out, but they're starting to be adopted. A couple states already have them, but the government is adopting it at the end of the year, so be aware of what's coming with that. we don't want to design just minimally legal buildings, right? We want to go a little bit beyond. So there's the government, they've got their codified stuff referring to 90.1. We won't get into that too much. So Architecture 2030 is a challenge that a lot of companies have adopted. Essentially, we're aiming for carbon neutrality by the year 2030. And so every 5 years or so, they update it. And right now, we're supposed to be 70% carbon reduction relative to a 2004 standard. Correct me if I'm wrong there, but I think that's right. So it's an aggressive goal. And I would venture to bet most of our projects aren't there. So this for it includes on-site renewable technology and also the load reduction that we'll talk about more here. All right, so navigating the rapids. You know, enjoying kayaking, I relate all things to that. And when you go to a big rapid, something that's going to be challenging for me, I want to see what's happening in the rapid and understand my line through it. If I miss my line, I end up bobbing downstream upside down or something like that. You end up in a place where you're not effective. Same thing with a project. You want to know your path through the project so you're not getting lost and missing opportunities and that sort of thing. So first thing, get started. I would say as soon as there's a project, you can get started. We don't need a floor plan. Maybe a rough location and building usage is all we really need to get started on a project. Know your codes, obviously. That's your starting point. We're going to try to go beyond that. And then set some energy goals. We can start with Architecture 2030. That's kind of a stretch goal in some cases, depending on the budget. Ultimately, that's where we want to be, and we've kind of committed to that as an industry. But Energy Star is another good source for coming up with some goals. So here's our he's getting ready to get started on a project. He's got all these inputs in his mind. We got to have a functional building, but we want it to be energy efficient. We want daylight. We need reasonable maintenance. There's all these things that we're trying to consider early on a project. And our job as energy modelers is to kind of identify some of these challenges and take some of these off the table and define these, start to quantify all of these so designers can do their job designing and not have to worry about all of these concerns. So ASHRAE came out with a standard, it's a proposed standard at this point, 209P, to define the energy modeling process. And they've got a 7-step process where you start with a box model, and the box model tells you some basic information, and then as the architect gets down the road, you have some concepts, and so maybe we have 3 different concepts, and we're trying to figure out, what has an impact in that concept model, and then we're trying to ultimately reduce the load. And then from there we can select systems and then start to refine the design and work together with other systems. And at the end there's a value engineering process. Well, the 7-step process, I can't remember. It's too many steps for me. So I whittled it down to 3. And load reduction, I think, is really the goal of the first 3 steps of ASHRAE 209. We're trying to figure out what has an impact in terms of building systems. Is it wall insulation or roof insulation or windows, or what's going to have an impact in our building? And we want to focus on that, and then maybe leave some other parameters towards code minimum, prescriptive code minimum. And then once we've reduced the load, we can start to look at our systems in more depth, and then refine it as the project goes. The value engineering side of things, in my opinion, that needs to be done throughout the process. We're not picking the most efficient system always. We're picking one that's efficient and cost effective, and we'll talk about that balance a little more down the road. But it's ideally that should be balanced along the road. Though we've got cost estimates and energy calculations wrong before, and so that does wind up at the end of the project in CA sometimes too. Okay, load reduction. What we're really trying to do here is reduce the number of unknowns in a project. We want to know, like I say, what has an impact, what doesn't. And we don't want to be reacting to the architect or the engineer. We want to be giving them information prior to them making those decisions. So we're trying to influence design rather than react. And in my mind, this is really true value engineering. And just for kicks, this sketch is that Sensi office tower on the Sensi campus, and this was our early SD. And I mean, at this point, we can be getting some real good information out of a model like that, even though that's not how it actually ended up if you've gone down Eagle Road in the last 3 years. To start off with, it's part of the load reduction process. I like to just start looking at the climate. In Boise or something, we all are pretty familiar with the climate if we're doing a local project, but oftentimes it's outside of Boise and we're not real familiar with it. So I can start to plot all of the temperature data. So up here I've got my temperature distributions by month with the 1% high and the 1% low. And right away, a lot about a building. I can know if it's probably going to be heating dominated or cooling dominated, and that can help me define some of these strategies down the road. Typically I figure a balance point for a building, and that's the point outside air temperature when the building switches from heating to cooling. Typical office building is probably 60, 65. There's a lot of fluctuations depending on building type, but just rule of thumb really early in a project in that perspective. The psychrometric chart for you architects and things, it's probably kind of gloss over, but there's a lot to gain. We've got temperature across the bottom, we've got moisture levels in the air on the vertical axis, and we can tell how many hours are in what region, and we can look at things like even night flush or passive strategies where we have to deal with dehumidification loads or humidification loads. And real quick, we can develop a lot of strategies that seem to carry fairly well into later phases of the project. And just a quick note on weather. A lot of times TMY3 is great. I mean, it's not always accurate, but it's close enough for this level of the project. But I have found, and I'll show you an example later in Nevada, that the TMY3 data doesn't get you close enough, that there's a very different microclimate that will have a big impact on the performance. So pay attention to that and make sure you're using something specific to your site. So let's start with the box model. This is the first stage in ASHRAE and in option as part of the load reduction process in my mind. So it's a really simplified model for estimating sensitivity or design parameters. I usually use for initial load or preliminary system selections. This is it. I mean, this is a visitor center. Just through the floor plan, where zoned it for me. And in half an hour, I have a functional model that can tell me just the basics on what's going to be impactful for this building. Okay, so the box model, I've mentioned a bunch of times, what has an impact. And the charts here, I'm using, I guess, quick disclaimer, my tools of choice are generally Autodesk, eQuest, and occasionally Energy Plus Open Studio. So I do have a little bit of bias in terms of outputs and how I look at things. But out of Autodesk, I'm getting these energy cost ranges. And somewhere down here, kind of in the middle, is a baseline building, basically what I've specified as what I think this building will probably end up being. And anything to the right represents an increase in energy consumption, whereas anything to the left would be an opportunity for energy reduction. So real quickly, I can look at all these different parameters and, for example, infiltration here. You know, if I really loosen that building up, it's going to kill me on energy. Let's make sure we have a tight building, or at least minimally code compliant. Like roof insulation. There's a lot to be lost if you go below code, a lot below code, but there's really not a lot to be gained in terms of adding insulation beyond code. This is for this specific example. I don't remember which one this is, but that'll depend on climate zone, so don't take that for all projects. We look into window glass, and a lot of times that has the greatest impact on an envelope, making sure you get your quantities right, your locations of glass, the glass types, and how it's working with lighting and that sort of thing. And in general, you do want some good daylight, and I understand views are important. I don't want to live in or work in a dark box, so you need some light. But in general, I've been finding that as low as you can get with the glazing, the better the energy performance ends up. And then as far as solar heat gain coefficient and shading your glass, in general, in climate zones 5 and 6, I don't always find that low E glass, real reflective glass, is helpful. A lot of times we want some of that solar in, but again, that depends a lot on your building type and your distribution of glass. So to dig into it a little deeper, see doing this kind of box model for sensitivity. I have a whole bunch of different things on different parameters, and I can start to see where the inflection point is. This one's infiltration, for example, and coming from I think that's a 2 air changes per hour building in terms of the energy model, not necessarily code infiltration, but it's pretty steady through there. Cutting down infiltration is a good deal. In terms of roof construction, no insulation on a roof, just roofing material. It hurts you quite a bit, but as you add a little bit of insulation, it kind of levels out. And so we can put R100 on the roof, and it might just gain us a little bit. So those are the things I like to look at. You can see those inflection points. And then you can develop a bunch of different alternatives with these plots and come up with maybe a code compliance strategy, a best practice strategy, and then a kind of a high performance strategy. Here's a kind of example I did. We were looking at thermal mass in the Pacific Northwest, and what really makes a difference on this was for wall construction, but it's the same with roof. And so I looked at it in terms of square foot per 10 degrees of temperature difference. So with the R1, we're up at the 10 mark BTUs per hour. And when we get to the R20, we're half or something like that. So it's a major reduction. And as I keep going out to higher numbers, it kind of levels out as it approaches 0. So there's really not a lot of benefit. So what we're looking at then is, am I going to go with prescriptive code levels, or am I going to drop it even lower? Or what do I want to do here? If I go below, I'm going to have to do some performance-based modeling to show code compliance. But maybe I can invest that extra money somewhere else in, say, lighting systems or mechanical or something like that. So already we're starting kind of the value engineering process. What has an impact? What's most cost-effective? Any questions, comments on that box modeling strategy before we move on? Okay, concept modeling. This really isn't a whole lot different than the box modeling, in my opinion, but not real forms. We have some blocks. Maybe there's a few different occupancies within a building. We can start to place those where we want them. We're starting to look at where glass is on the building where we want it, where our views are, and that sort of thing. But still, we're trying to reduce loads at this point and maybe start to look at systems at a really high level. So when we get into this phase, you got to make sure that you're an architect. I mean, most of us engineers struggle with this. So I've attached this do-it-yourself architectural dialogue, so you can create your own gobbledygook statements that sound profound. So I'll leave that here for you, refer to in the future. But I mean, it's a serious consideration. As engineers, we want efficiency, we want things to work for our systems, but there's a lot of aesthetics that go into it. You want a building that looks nice, is functional. There's all sorts of other considerations here. So we want to know how the form influences the performance, and we'll look at it a few different ways. And over on the right there is an example. This is just a generic office building, and we wanted to look at just aspect ratios of an office building. And so we looked at 1-to-1, just a box, and we moved down to the 3-to-1 ratio. And in this case, we're not really taking full advantage of daylight dimming and things like that. I think you'd see see this one start to creep down if we really take advantage of that. But essentially here, the impact is fairly minimal on the aspect ratio of this particular office building. So these are some things we can tell the architects right up front that, maybe the aspect ratio isn't that big a deal from an energy perspective. Do it as you think is best for function and aesthetic. So some of these things we can just start to take off the table. Let's not worry about that. Let's worry about this. That's really our goal here in the concept model. And then another one to consider is how you're distributing the occupancies. For example, a school is going to have a big gym. where do you want that? Do you want that on the south face or the north face, or where does that go? What's the most efficient way to do that? You know, the south, you can kind of control the solar, but there's a major load. Do you want that in your gym, or are we just going to make it a box and you do your skylights, so it doesn't really matter where it is? You can start to think through some of those things. Again, glazing is generally more important than the form in my experience. Okay, system selection. So ideally in the previous phase, we've looked at all the different loads and we've reduced it to a reasonable level. And from here we can start to really dig into the systems. And by systems I mean lighting, HVAC, glazing, shading, that sort of thing, where we're trying to really dial it in a little bit more. In my opinion, this ought to be accompanied with a life cycle cost analysis or some sort of cost evaluation, because energy is not always the top goal of a client. We want something that's easy to maintain, efficient, not that expensive up front, and the ranges of all these vary from client to client. How far into the future are we willing to push the payback and that sort of thing. But yeah. So once we're in this phase, you can start to address the loads that we've been working on in the previous phase. So again, an Autodesk output, but we can start to visualize the loads. In this one, window conductance is the biggest deal. Well, what can we do with that? Is there anything we can do with that? You know, maybe it's adding some shades on certain exposures. Maybe that's what we're stuck with. So, I'm sorry, we can't shade on conductance, but maybe we can reduce it or go triple pane or something like that. But if this is our load, we can see we're heating or cooling, and we can start to pick our systems based on for heating or cooling dominated. I don't want a super efficient cooling system up in Alaska. I mean, we're not going to use it. It's going to save just a little bit of energy, and it's going to cost a lot more. So how do I pick a system that is really going to be right for this site? And then looking at heat rejection or other opportunities on the site. Alaska, for example, you've got cool weather year-round. It gets cold at least at night. Can you use that just as use the air and flush the building out so you're never really cooling? Or maybe you have a pond on site, or all sorts of property. You could put ground loop heat exchangers or something like that. So something to look at. A lot of times those kind of unusual heat rejection ideas aren't cost effective. Sometimes they are, depending on the needs of the project. And then I guess loads would be the other one. A data center, for example, would have a pretty consistent load profile, and there's some things you can do with mechanical equipment to just maintain that. Other times an office building or something like that has a real variable load, so you want your equipment to be able to handle the variations in load and keep spaces comfortable at the same time. Here's a case study on, this is an office in a data center in South Dakota, and they needed a new roof. It was a 20-year-old roof or something like that. So they had to go in and replace it anyway, and the existing building had an R20 roof, and I think current code was an R30 or somewhere in that ballpark. So we're looking at an R30, and what if we added a couple more inches for an R42? What's the payback, and what should we do for something like this? Well, it turned out to go from the R30 to the R42 it's almost $100,000 in materials cost. It's a pretty big building, and it's internally load dominated, so we weren't really needing that much heat, or we weren't. Yeah, we weren't needing a lot of heat in the winter because the loads were really keeping it up. So we ran the energy models, calibrated it to actual data, and I found about $260 a year we'd save in energy costs if we had another R12 to the roof. For $100,000, you can save pretty quick, but that's not a good investment. So these are some of the things we want to look at in the energy model to try to inform these decisions. Otherwise, it would just be opinion talking about the roof insulation. So then HVAC system analysis. When we go into a project, I like to have 3 or 4 different alternatives that we're looking at. We'll probably have a low-cost option, a more typical best practice option, and then a high-performance option at minimum. And you can have all sorts of different alternatives worked into there. For example, heat recovery on a system, or all sorts of different configurations. So that's what this is. This is one where we started with a baseline, and then we started doing things and reducing the load, and then over here we have all the systems that I tried. I recommend doing a schematic or something like that, whatever works for you, just so you can visualize all of the energy consuming components and make sure you're accounting for them in the energy model. Yeah, and so I guess the next question is, can the simulation software correctly simulate the systems? And most basic systems, any software can do it. But a lot of programs, even we found Energy Plus has its limitations with certain systems. So you either have to go outside to a spreadsheet or some other way of calculating these measures. EMS Manager in Energy Plus sometimes works, but something to consider here. Quality results really depend on your assumptions. If you're using all the eQuest defaults, for example, there's going to be something in there that's going to be way off potentially. So know your systems. And at this point, I kind of recommend that this be an engineer, or at least have an engineer looking over your shoulder, because you need some mechanical background to really dig into some of these. And then following it up with a kind of cost-benefit analysis. You've got all these things. You've got energy, first cost, you've got maintenance costs, operations, practical things. All of these things go in. Even life cycle materials I've been seeing kind of gaining traction in the industry. So we want to get these all into one common metric. And life cycle cost is usually a pretty good way to do that. And you can plot out, for 15 years or however long you want to look at it, what are all the costs associated with this building? And then you can bring that all back to present value and compare it that way. And it's really just an apples to apples comparison. And just to be clear, life cycle cost analysis and life cycle analysis, I keep seeing those mixed up. Life cycle cost is exactly what I'm talking about. Life cycle analysis is when you're looking at building materials, and let's say I got my cement from Portland and I've got my wood from Utah, and you're dealing with all of the energy and costs associated with that, and that all goes into a pool. That's a different kind of analysis that I'm not going into detail here. Richard could tell you all about that. Yeah, good question. So the question was what software do we use for lifecycle cost analysis? There's all sorts of tools out there. The DOE has published this BLCC 5, or maybe we're 6 now, I don't know. But they've got a software. I think it's kind of a black box. You put your inputs in, and then you get something spit out. I don't love it because I can't understand what's going on. Back in the the early 2000s, somebody came out with a spreadsheet version of that, and you can find that on the eQuest homepage, do2.com. And so they call it the user-friendly lifecycle cost spreadsheet. And they've got fuel escalation rates and inflation and things like that built in. Those are also things that the DOE publishes every year, so you can go through and update that. That's one source. I know the city of Seattle has their own life cycle cost analysis tool for free download. There's all sorts of tools out there, and really the math isn't that hard. It's economics, but the escalation rates and things like that are a little bit trickier, and I like to go to the DOE for that information. They also have 10 CFR 436, I believe, which is the government's requirements for life cycle cost. So let's give you some guidelines. Design refinement modeling, which is kind of my last stage here. I'm looking at the systems we picked and trying to figure out how can I make this system better. Can I update the sequence? Can I add a little bit, a sensor or some other piece of equipment here or there to do that? Maybe we decided we wanted 2% skylights on a roof. Now, what if I go to 3%? Does that help my energy or my daylight a little bit? Those are kind of the questions we're looking at in this phase. And this is exactly we had a big warehouse we did, and I don't remember the percentages exactly here, but we had one iteration where we had some spotty daylighting. Pretty well covered, but definitely some holes. And then here's definitely the better solution from a daylighting perspective, even distribution. but what does that mean in terms of energy? And so we threw that into eQuest a few times and ran a few iterations and settled on a daylighting level that we could live with and an energy level we can live with. We're balancing lighting reduction with increased heat transfer through the roof. And then I kind of see this as a little commissioning exercise. A lot of times we do commissioning in the field where a third party comes in and they test all the equipment, make sure everything's operating the way it was designed to. Well, we're really doing this in the energy model too. Once we have a design in there, we can try to tweak the sequences, and maybe we find that there's this room here that is freezing most of the year. Well, can we adjust some airflows or some controls to try to get that room to work? And I can really dig deep into sequences and see what the best way to do things is. And just things as simple as meeting the load. Maybe our equipment's undersized and we're not going to meet the load for 1,000 hours in the summer. And that's something we can address. And sometimes it's just a simulation issue. You know, you make a tweak, something was entered in wrong. But a lot of times it's really a good QC check for you and the engineer. All right, final documentation, and we could model for LEED and green globes and code compliance and things like that, but I'll touch it with a slide here. In my mind, this is the most time-intensive piece of energy modeling because you're trying to get every last piece correct size, correct manufacturers, curves, airflows, that sort of thing. And it takes a lot of time to go room to room and get all that right. So keep that in mind. And I mean, at this point, we probably have the least amount of impact too. It's another QC at the end, but we're really not influencing the design. LEED is requiring, I shouldn't say requiring, they have an optimized energy credit, which has been there for a long time, but they also have the integrative design process. And that particular credit requires some very specific modeling exercises similar to the box and concept models up front to show you what has an impact. So you make sure we're documenting those. Green globes, federal government, they all have their own requirements, and we can get into more detail if we're interested in that. Custom utility incentives, talk to Chris, other utilities have similar requirements. And then Energy Star, we can go in afterwards. They actually require some real data, but they also have the designed for Energy Star certification. You can do that with an energy model. And then we always want to check how we're doing against Architecture 2030. They use Energy Star, but they also have some documentation on how to benchmark these things. And then code compliance. If I decide I want to go outside of prescriptive code measures in a building, I can choose to energy model to show compliance. 90.1 has the energy cost budget method in Chapter 11. Those are your guidelines. They actually have some forms associated with that you can just fill out. And yeah, so that's different from Appendix G. There's some pretty specific differences. And I think by 2016, ASHRAE 90.1, they plan to kind of merge those into one for code compliance. And then IECC has a section C407, if you're interested in that. And then Title 24 and other entities have their own requirements that you need to be aware of. All right, post-occupancy. I hear a lot, why do we model? They're not accurate. Who cares anyway? So I think the biggest thing we as modelers and design professionals can do for the industry is to go get your data afterwards. You're down the road, at minimum, just go get your utility bills, compare it to the model, see how it did, and then and share that, because we want to know how our models are working. It helps us, helps the client, helps designers. It does put you at a little bit of an uncomfortable spot. If you predicted we're 20 UI, we ended up 40. It's kind of scary going to the client, but I think it's something we need to learn one way or another, why it isn't performing the way it should. And sometimes that's an opportunity for improvement in the building. Maybe a piece of equipment wasn't set up right, and quick fix can get them up and running again. So I just threw in a few here. This is a bank we did in Cody, Wyoming, and some of my examples are a little outdated here, but a bank or an office building is kind of your ideal situation. You know, everybody works 8 to 5. You know roughly the number of employees. You know systems pretty well. They're usually not real complicated. So in this case, the blue is my original energy model, and excuse me, the orange is my calibrated model. There's really not a whole lot of difference there. So this is kind of a, excuse me, kind of your ideal situation. Very high correlation between the two. Here's an example of how occupancy really influences a building model. And as modelers, we're kind of like weathermen, right? We're trying to predict something in the future that we really have no control over. We're trying to predict occupant behavior. We don't really know how people are going to use their building. They have an idea, but things change. And we can't predict the weather, obviously. So in this case, this was the College of Southern Idaho Health Science building. We were told to design for a year-round school situation, a lot of medical training going on. And it turned out they didn't want to do that anymore. They're just going to stick to the typical off for the summer schedule. So I have this big spike showing in the summer. It didn't happen. They're not using the building. So with quick calibration, we're able to fix that. But there are some things that are off. It's not always perfect, but it's fairly close. Here's a supermarket we did. I think this one was in Austin. And we were pretty close here. We got the trend fairly close, but we were significantly lower than they ended up using. And I think when you have refrigeration systems and heavy exhaust systems and things like that, there's a lot of things that are hard to model. I think this one ended up having a parking garage attached, which may have had something to do with it too. So, yeah, a couple examples. And to give you, we'll run through these real quick. This is just a case study to see this process working out. And all of those different slides I showed you on the box model and the concept model, I wouldn't say you necessarily have to do all of these on every project. Think of it in terms of what a project's goals are and what makes sense in terms of budget. So for this one, we've got a visitor center near Alamo, Nevada. We're about 90 miles north of Vegas. And 5,000 square feet, $3 million, 4 acres. Design build, we were going for LEED silver. We were required for that. But they also wanted to see what we could do to get to net zero on that budget. So starting with the architects, we've got our site. We have kind of your touchy-feely stuff, your sun patterns, your views, where's the wind coming from. And we throw just here's a box. We want parking roughly here. We might have a pond here, and we've got good views. So this is kind of what we want to see. So at this point, I start looking at the weather, and this was the example of a TMY3 set. I just found the closest TMY3, which is typical meteorological year. They've got 1,000 locations around the country or something. And it was 90 miles, 100 miles away, and it was way off. The peak temperatures were 110, 115, and it never got below freezing. But just that 100 miles away, we were in the high desert, kind of out of the Mojave Desert, I think. And it really cooled down quite a bit and ended up being a lot like the Boise climate. So early on, we made a few assumptions that were incorrect and had to go back and fix that. And I know Chuck appreciates my scatter plots, but there may be others that don't like that as much. There's all sorts of different ways. Data visualization is an important thing. You probably wouldn't show this one to the client. So right away when we had that box, I could start looking at different ideas that we were throwing around, passive strategies. And this one is mass. So to break it down, the blue here is the outside air temperature in both. This is February, which happened to be the peak cooling day, or peak heating today, and this one is in July, which happened to be the peak cooling. The green here is a code-compliant frame wall. I don't remember if I think we were stick frame here, and then the red one was a thermal mass, and I think we're looking at about 8 inches of concrete, so a significant amount. And what we're trying to do here is reduce our cooling load primarily in the summer. The thermal mass will delay the load quite a bit. So if we look at, here's your peak temperature outside, well, the peak load into the space doesn't happen until, I think that's about midnight when people are gone. So it's perfect for cooling. You cut down your loads and it kind of evens things out at the same time. Well, on the heating side, the same is true. So the peak cooling temperature, or heating temperature, happens at, what is that, 4 in the morning or 6 in the morning or something. And that load is now, so we're looking at most negative now for your heating loads. And that's now transferred to, 10 or 12 in the morning. And so now our mechanical system's having to account for all that extra heat. So in this case, we found it almost to be a wash between a stick frame and the mass. And the mass is quite a bit more expensive, so we decided, it's not worth the investment in this case. Let's go with just a stick frame building, fairly well insulated. And we started playing with this kind of early concept model where we knew we had kind of a interpretive center in the middle. We had offices on one side and then a conference room on the other side. And we flipped it around a couple times and we found that, this really doesn't work very well from an energy perspective because you can't control your solar in the morning and the evening and you're getting all sorts of glare. So this isn't ideal. This is really ideal. So we ran with that concept a little bit. And at the same time, I'm running all of my different alternatives. This was before I knew how to use the cloud computing that Autodesk lets you do. So I'm running these by hand. Well, we came to kind of a compromise here, where we have some of that east to west instead of the north-south. But we still have our views. We have a good amount of glass here. We can look out and look at the scenery, potentially the pond, which we didn't end up having, but you still have some good views. And then I was able to come up with a system and compare it to the baseline. So we had some early results, and we came up with this concept. This was a design build, so we were working with the contractor and the government at the same time to try to come up with the right solution. So we had this idea of natural ventilation. We could handle a lot of our cooling loads with that, and radiant systems. We were using the pond out on the site for heating and cooling. And I modeled around just under a 20 EUI kV2 per square foot, which is very low. Well, talking to the contractor, we found this to be fairly expensive. So what it comes down to, and credit to Energy Center Wisconsin here, the net zero energy balance. So early on, a code minimum building, this is roughly where you stand. There's a fairly high energy consumption, and your construction cost is also fairly low. While early on you can do some just basic measures, doesn't cost any more, might even save you a little bit, and you reduce your energy a little bit. Well, after that point, you start applying some proven measures, and the slope here is pretty good. We're saving energy, it's not costing too much, but just like the insulation, we hit this kind of practical minimum where we have really complex and expensive measures to save just a little bit of energy. So we want to stay somewhere around here. And on the flip side, we're generating energy on site. So we've got a PV array in this instance. And initially you have some infrastructure that you need. You need inverters and things like that, roof racks. But as you get to be a bigger system, there's a little bit of an economy of scale. Costs go down a little bit with your energy generation. But eventually you run out of roof space, for example. And you got to put in more infrastructure to add more PV. So we don't really want to do that. We want to keep it on the roof. So we're trying to find that balance here. And it's really just this sweet spot here. So that ended up being the goal. And working with the contractor to try to figure out what was cost effective for him, being kind of 90 miles out in the middle of nowhere, we had to consider how to get things there, how they're going to be maintained. So we ended up with a small ground loop heat pump system. Essentially, the heat rejection is 10 feet underground, and you set it in there. It's plastic pipe that's essentially good for a long time. Then you've got basically residential light commercial heat pumps inside. Anybody from the region knows how to maintain those fairly well. So we ended up at a model DUI of 26.3, which is a little higher than what we were initially targeting, but still pretty solid. And we were even able to set up some net metering with Alamo Power, the local co-op. And so they're actually getting paid for the excess they generate. So it ended up being a pretty good deal. And after a year, and it's about time to go check in after here, here's our results. So the top here is my modeled performance in the blue line there, and then the bars are what we actually ended up using. And they ended up using a lot less than we expected. And I think essentially they didn't add the biologists they were kind of expecting, and they probably didn't have quite as many visitors. And it takes a little while to get things up and running. So I'm interested to see where it lands this coming year. But essentially they use about half as much as what we expected. And then on the PV side of things, orange being the PV model and the bars being what they actually produce, we were pretty close except in the spring and summer there. And we found we were actually submetering 4 different usage types: PV, HVAC, plug loads, and lighting. And so I was able to look at kind of a granular level what was going on. Well, they had breakers popping on their PV panels. So they were down to, we had 3 arrays total, and down in most of June, they only had 1 array in operation. So working back with the contractor, get those up and running, they seem to be doing a lot better now. And I've been continuing to monitor the sub-meter data, and that continues to perform as expected. Okay, so wrap it up here. Know the rapids. It's a lot of fun when we know where we're headed. We want to have a plan on every project. Get started early, and really, you don't have to be ridiculously good looking to model. Anybody can do this. So, and then finally, I guess, follow up with that utility data when possible. It's important for us to share and at least find out internally how our designs are doing. So with that, I'll open it up to questions.
Talk a little bit about your zoning strategy, pre-models as you move out of that into the more detailed models and all that kind of stuff. So that you're really granular, actual HP zones, and then you can have something change.
Yeah.
So what's your approach to that?
Okay. Sure. So the question was, how do you handle early on? We probably want a real simplified zoning process. We want our model to run quick. We don't want to spend a lot of time generating the model. So I usually just stick to kind of a perimeter core scenario. We do a lot of visitor centers and things like that, and with a 5,000 square foot building, it's really not that bad to do just about every zone. But if you're dealing with a larger office or a hospital or something like that, you don't want to go through and do huge spaces like that. So try to set up your blocks within reason. I try to think of how I might lay out my HVAC system and lay it out that way. But you're right, as you move into more construction documents, you're having to document every last zone in a lot of cases. And that can be pretty time consuming. And with an eQuest type software, you can't just change that easily. You're essentially starting from scratch. So definitely something to consider. I don't know if I have a solid answer for that. Do you have any suggestions? I think some of the other software programs, and especially if you're working with Revit and you figured out that interaction, ideally you can be continually updating the zones and your model, but we're not there yet.
It's just an antagonist.
Okay.
Oh,
I worked in all of Chuck's favorite things: scatter plots, Zoolander, and
I was going to
kayaking.
ask if you find scatter plots aesthetically pleasing.
I do. I think it's kind of engineering artwork. What do you guys think? Yeah. That's right. Yeah, you gotta see the trends, right?
So how often do you use energy modeling for code compliance? Do you mainly use energy modeling for lead documentation, or sometimes for code compliance as well?
Yeah, that's a good question. So I've seen some changes in our company, at least. Initially, I kind of got into energy modeling for lead. This requirement for lead, we did it on quite a few projects. Then we found out government required it for just about every project. And so that's another kind of documentation modeling with some life cycle cost. with some of these early modeling concepts with Autodesk workflows and things like that, it gets to be really fast. And so within an hour or two, I have a functional model that tells you just, I mean, not in specifics, but big picture, what do we need to be considering for this project? I've been finding most projects can handle that level of modeling. As far as the code compliance goes, I think with this latest code iteration, I've probably done 3 code compliance models and, I don't know, 20 or 30 other types of models. So it's definitely the minimum, or a small portion of what we do. But I've been finding economizers are an issue a lot of times. The code requirement for cooling capacity, where you need an economizer, is getting lower and lower. So some of these, like a VRF system, it's hard to do a VRF system without figuring out the economizer situation. So that's triggered a code compliance model. And then a couple others, I guess one is the window to wall ratio. Code only lets you go to 30 or 40% window to wall ratio, and a lot of buildings are going higher than that. So anytime you do that, you pretty much have to go with the energy model. Yeah. Anybody else? I'd be more than happy to talk software or code or whatever you want afterwards.
No more questions? Thank you all for coming, and we hope to see you next month.